Welcome to part 2 of Corona Calculus. Oh boy, it's continuity time. So this is going to be part 2 of Corona Calculus, where we go over continuity. Today we'll be going through definitions, properties, and the intermediate value theorem. So it should be quite quick, short video. Let's get started. So, I guess many of you guys have heard of continuity before. Something like it never breaks, or you don't pick up the pen. Well, let's do some formal definitions of continuity. So we say a function f of x, f of x is continuous at a point C. So like x equals to C. If we say this implies that the limit as x approaches C of f of x equals to, well, f of C. It's pretty cool. So this doesn't seem too useful because we want to express continuity on a whole function. So let's just say, when we say f of x is continuous on the interval, open interval a comma b, this implies that for any, let's say D, since we already used C, D that is in the set A, B, that f is continuous at D. So basically we're using this definition of a point and applying it to all the points in this interval. Lastly, we have the case where f of x is continuous on closed interval a, b. So this is the same as, well, first you need to have that f of x is continuous on the open interval, and you need to have that the limit as x approaches a from the right or the positive side of f of x equals to f of a, and the limit as x approaches b from the left side or from the negative side of f of x equals to f of b. So you need both of these conditions to satisfy continuity on a closed interval. Okay, so some more definitions. I guess you just saw me use the definitions of one-sided limits. One-sided limits will be used quite quickly in these definitions. So limit as x approaches C from the positive side is from the right, and limit from x approaches C from the negative side is from the C from the plus is right, and C minus is from the left. So we have another theorem here that we can use using these definitions, that the limit as x approaches C of f of x exists if and only if limit as x approaches C from the positive side equals to the limit of f of x equals to the limit as x approaches C on the negative side of f of x. So these two have to be equivalent in order for this to exist. That makes a little bit more sense, doesn't it? Okay, do some quick examples. So let's say f of x equals equals to the floor of x. So we can say that this is continuous on the enclosed interval 1 and say 3/2, right? And this is continuous on the 1/2, interval 1/2 inclusive and 1 exclusive, right? But this is clearly not continuous on, say, the closed interval 1/2 and 3/2, because 1 is not continuous. Well, sorry, f of x is not continuous at 1. Right. Because of our theorem here, we can say that from the right, f of x approaches 1, and it will be equal to 1. The limit as x approaches c, or 1 from the positive side, is 1. And the limit as x approaches 1 from the negative side is 0. So therefore, the limit as x approaches 1 of f of x does not exist. Okay. Now for some properties of continuity. So, let's have f and g. Let them be continuous and be from the reals to the reals, and k be an integer, or sorry, a real number. A real number. God, I can spell. Alright, so assuming these, we have that the following are continuous. So we have that k times f of x will be continuous. These are just multiplying it by a real number. We say that f plus g is continuous. F times g is continuous. And lastly, f divided by g is continuous. You can prove all of these using limits, but we will not be proving them in this video to keep it short. So, another important thing to note is, therefore, all polynomials are continuous and all rational functions are continuous. That's important, and we'll be using that later on. Now, let's do a theorem. This was not in the topics, but it's a useful theorem. So, if we have that g is continuous at c, f and g are continuous at c, then f of g of c is continuous at c. So from this theorem, we won't be proving any of these theorems for this video, but from this theorem we can see that limit as x approaches c of f of g of x equals to the f of the limit as x approaches c of g of x. So these two are equivalent by this statement. So now this is very useful because we can apply limits outside and inside functions as long as they are continuous on the constant c. Okay. Now for one of the first big theorems in calculus, the intermediate value theorem. If I can spell it, probably not. Value theorem. also known as the IMVT. Okay, so what is the IMVT? Let's see. So we need to have first some definitions. So let f be continuous on the closed interval a comma b, and without loss of generality, let f of a be less than f of b, strictly less. So the intermediate value theorem states that for any k in the interval, closed interval, f of a, comma f of b, there exists a c in the interval a, comma b, such that f of c equals to k. So besides the symbols, we can draw a little picture to make it easier to see. So we have, let's see, A and B. And so we have f of A here and f of B here. So we have 2 points. Okay. And so we're saying K is somewhere here, right? And basically the argument is by continuity, for every value of k in the y, there must be a value of c in the x. So say k is here in the x, such that f of c equals to k. We won't be proving this. This requires a lot of hard stuff to prove, sadly, and I'm not good enough to do that. So that's it for continuity. We'll be back with limits and infinity.